Welcome everyone. In today's video, we are going to understand one of the most important fundamentals of centrifugal pumps, the pump performance curve. Whenever a pump is selected for an industrial application, engineers don't rely only on its flow rate or power rating. Instead, they refer to the pump performance curve to understand how the pump will behave under different operating conditions. In this video, we'll learn what a pump performance curve is, how manufacturers develop it through performance testing, and what each parameter on the curve represents, including flow, head, efficiency, brake power, shutoff head, runout, and NPSH required. Finally, we'll briefly introduce the affinity laws and see how changes in pump speed or impeller diameter affect pump performance. So, let's begin by understanding what a centrifugal pump performance curve actually is. Before we learn how a pump curve is developed, let's first understand what it actually is. A centrifugal pump performance curve is simply a graph that shows how a pump performs under different operating conditions. It is developed for a constant pump speed and a fixed impeller diameter, so any change you see on the graph is due to a change in the flow rate. Now, let's look at the graph shown on the slide. This is a typical pump performance curve supplied by pump manufacturers. Although it may look complicated at first, it is actually very easy to understand. As you can see, the graph contains multiple curves. Each curve represents a different performance characteristic of the pump, such as the pump head, power, efficiency, and NPSH required. Together, these curves provide a complete picture of how the pump behaves throughout its operating range. Now, how do we read this graph? We always start with the flow rate, which is shown on the horizontal axis. Once the required flow is identified, we move vertically upward until we intersect the performance curves. From those intersection points, we can determine the corresponding values for head, power, efficiency, and NPSH required. For example, in this graph, if the required flow rate is around 50 cubic meters per hour, we move vertically upward to the pump curve. At that point, the pump develops approximately 35 meters of head. If we continue along the same vertical line, we can also read the corresponding power from the power curve. At this stage, you don't need to worry about what each individual curve means. The purpose of this slide is simply to understand what information a pump performance curve contains and how it is read. In the following slides, we'll discuss each of these performance parameters one by one in detail. Now that we understand what a pump performance curve is, the next question is, where does this curve come from? A pump performance curve is not calculated theoretically. Instead, it is developed by the pump manufacturer through actual performance testing. To ensure the results are accurate and consistent, these tests are conducted according to internationally recognized standards, such as API 610 and the Hydraulic Institute testing procedures. During the test, manufacturers use clean water as the test fluid because its properties are well known and remain consistent. This provides a standard reference for evaluating pump performance. To obtain reliable results, several testing conditions are kept constant throughout the test. The pump speed remains constant, the impeller diameter is fixed, and the measurements are taken using fully calibrated instruments to ensure accuracy. By maintaining these controlled conditions, manufacturers can accurately measure the pump's performance over its operating range and generate the performance curves that are included in the pump datasheet. But how are these measurements actually taken? In the next slide, we'll look at the complete testing process and see how the pump performance curve is developed step by step. In the previous slide, we learned that a pump performance curve is developed through actual performance testing. Now, let's understand the test setup used by manufacturers. This figure shows a typical pump performance test loop. The test pump is driven by an electric motor, and the electrical power supplied to the motor is continuously measured. The pump draws water from the suppression tank through the suction line. Pressure gauges installed at the pump suction and pump discharge measure the suction and discharge pressures, while a temperature indicator monitors the test fluid temperature throughout the test. After leaving the pump, the water flows through a flow meter, which accurately measures the flow rate. It then passes through the discharge control valve. This valve is one of the most important components in the test setup because it is used to vary the flow rate during the performance test. The water then returns to the suppression tank through the test loop. If required, a heat exchanger maintains the water at the desired temperature, while the vacuum pump and pressurized air connection are used during NPSH testing to control the suction pressure. During the test, the discharge control valve is gradually opened or closed to obtain different flow rates. At each operating condition, the manufacturer records the flow rate, suction pressure, discharge pressure, power consumption, and other required measurements. Each operating condition produces one test data point. By repeating the test over the entire operating range, a number of data points are collected. These points are then plotted on a graph and smoothly connected to form the final pump performance curves supplied by the manufacturer. So far, we have learned what a pump performance curve is and how it is developed through performance testing. Now, let's understand the meaning of the parameters shown on the pump curve. Each parameter tells us something different about the pump's performance. When these parameters are combined, they help engineers understand how the pump will behave under different operating conditions. Let's discuss them one by one. Head. Let's start with head. Head is the amount of energy that the pump adds to the liquid. In simple terms, it represents the pump's ability to overcome system resistance and move the liquid from one point to another. Head is usually expressed in meters or feet. It is important to remember that head is a measure of energy, not the physical height of the pump. Flow rate. Next is flow rate. Flow rate is the quantity of liquid delivered by the pump in a given period of time. It tells us how much liquid the pump can supply to the system. Common units are cubic meters per hour, liters per second, or gallons per minute. Efficiency. Now let's look at efficiency. Efficiency indicates how effectively the pump converts the mechanical power supplied by the motor into useful hydraulic power. Since every pump has hydraulic and mechanical losses, no pump is 100% efficient. A higher efficiency means less energy is wasted and the pump operates more economically. Brake power. The next parameter is brake power, also known as shaft power. Brake power is the actual power required at the pump shaft to operate the pump. This power is supplied by the electric motor and is usually expressed in kilowatts or horsepower. Selecting the correct motor depends on this value. Shutoff head. Now let's understand shutoff head. Shutoff head is the maximum head developed by the pump when the discharge valve is completely closed. At this condition, the flow rate is almost zero, but the pump generates its highest pressure. Continuous operation at shutoff is generally avoided because the liquid inside the pump can heat up and damage the pump. Runout. Finally, let's look at runout. Runout is the maximum flow condition of the pump. It occurs when the system offers very little resistance, allowing the pump to deliver its highest possible flow rate. Operating continuously near the runout condition is also not recommended because it can increase vibration and may overload the motor. These are the basic parameters that you will find on a centrifugal pump performance curve. Understanding these parameters is the first step toward reading and interpreting any pump curve with confidence. In the next part, we'll see how changing the pump speed or impeller diameter affects the performance curve using the pump affinity laws. Now that we've understood the basic pump performance curve, let's see what happens when we change the pump itself. Suppose the required flow increases, or we want the pump to produce a higher head. One option is to increase the pump speed. Another option is to change the impeller diameter. But how will these changes affect the pump performance? This is where the pump affinity laws become useful. These laws help us predict how the flow rate, head, and power will change when either the pump speed or the impeller diameter is changed. As you can see on the slide, the affinity laws provide the mathematical relationship between these parameters. But rather than trying to understand them only from these equations, it's much easier to see them in action. So first, we'll change the pump speed in the simulator. As the speed changes, we'll observe how the pump curve shifts and how the flow rate, head, power, and the operating point change. Once we clearly understand the effect of speed, we'll reset the simulator and repeat the same exercise by changing the impeller diameter. This will help us compare both cases and understand how each parameter influences the pump curve. Finally, I'll also demonstrate the effect of changing the discharge control valve opening. Although this is not part of the affinity laws, changing the valve opening changes the system resistance, which shifts the system curve and results in a new operating point. So, with that understanding, let's open the simulator and begin with the effect of pump speed. Let's begin by changing the pump speed. Currently, the pump is operating at its rated speed. This is our reference condition. Now, I'll gradually increase the pump speed. As you watch the graph, pay close attention to the pump curve, the power curve, and the operating point. Notice that as the speed increases, the pump curve shifts upward and toward the right. This means the pump is now capable of producing more head as well as more flow. At the same time, observe the power curve. It also moves upward, indicating that operate. Now, look at the operating point. Since the pump curve has shifted, the intersection with the system curve also moves. As a result, the pump operates at a higher flow rate and higher head than before. This is exactly what the affinity laws predict. Increasing the pump speed increases the pump's capacity and performance, but it also increases the power required from the motor. Now, let's move the speed slider in the opposite direction. As the pump speed decreases, the pump curve shifts downward and toward the left. The pump can no longer produce the same head or flow. Notice that the power curve also moves downward, showing that the power requirement has decreased. Once again, observe the operating point. It moves to a lower flow rate and lower head because the pump is now operating at a lower speed. So, from this demonstration, we can clearly see that changing the pump speed changes the entire pump performance curve. The head curve, power curve, and the operating point all change together. Now that we've understood the effect of pump speed, let's look at the second application of the affinity laws, changing the impeller diameter. Sometimes, the required pump performance is slightly higher or lower than the existing pump can provide. Instead of replacing the entire pump, manufacturers often increase or reduce the impeller diameter to match the system requirements. According to the affinity laws, the flow rate is directly proportional to the impeller diameter. This means that when the impeller diameter increases, the pump delivers more flow. Similarly, reducing the impeller diameter decreases the flow rate. The head developed by the pump is proportional to the square of the impeller diameter. So, even a small increase in impeller diameter produces a noticeable increase in the pump head. Finally, the power required by the pump is proportional to the cube of the impeller diameter. This means that increasing the impeller diameter also increases the power required from the motor. These relationships help engineers estimate the new pump performance without carrying out another complete performance test. The equations are useful, but they're much easier to understand when you can actually see the pump curve changing. So, in the next demonstration, we'll use the simulator to change the impeller diameter and observe how the pump curve, the power curve, and the operating point change in real time. Now that we've seen the effect of pump speed, let's reset the simulator and see what happens when we change the impeller diameter. At the moment, the pump is operating with its original impeller diameter, and this is our reference condition. Now, I'll gradually increase the impeller diameter. As you watch the graph, notice how the pump curve begins to shift upward and toward the right. This means the pump is now capable of delivering more flow and developing a higher head. At the same time, observe the power curve. It also moves upward, indicating that the pump now requires more power from the motor. Now, pay attention to the operating point. Since the pump curve has shifted, the intersection with the system curve also changes. As a result, the pump operates at a higher flow rate and higher head than before. Next, let's decrease the impeller diameter. As the diameter becomes smaller, the pump curve shifts downward and toward the left. The pump can no longer produce the same flow or head. You'll also notice that the power requirement decreases, and the operating point moves to a lower flow rate and lower head. This is why manufacturers sometimes trim the impeller when a lower pump performance is required. Instead of replacing the entire pump, reducing the impeller diameter can adjust the pump to better match the system requirements. So, just like changing the pump speed, changing the impeller diameter changes the pump performance curve, the power curve, and the operating point. However, in this case, the change is achieved mechanically by modifying the impeller size rather than changing the pump speed. So far, we've seen how changing the pump speed and the impeller diameter affects the pump performance curve. Now, let's look at another important concept. Changing the control valve opening is not part of the pump affinity laws. The pump itself remains exactly the same. Its speed does not change, and the impeller diameter also remains unchanged. Instead, changing the valve opening changes the resistance offered by the piping system. As a result, the system curve changes, while the pump curve remains unchanged. Let's see this in the simulator. First, the valve is at its normal opening, and this is our reference condition. Now, I'll gradually close the control valve. Watch the system curve carefully. As the valve closes, the system resistance increases, causing the system curve to become steeper. Since the pump curve remains the same, the operating point moves to the left. This means the flow rate decreases, while the pump develops a higher head to overcome the increased system resistance. Now, let's do the opposite and open the control valve. As the valve opening increases, the resistance in the piping system decreases. Notice that the system curve shifts downward. Once again, the pump curve does not change because the pump is still operating at the same speed with the same impeller diameter. However, the operating point now moves toward the right. The pump delivers a higher flow rate, while the required head decreases. This demonstrates an important difference. Changing the pump speed or impeller diameter changes the pump curve itself. Changing the control valve opening does not affect the pump curve. It only changes the system curve, which results in a new operating point. This is the principle used in many industrial systems to control the flow rate without modifying the pump. And with that, we come to the end of this video. I hope this presentation has helped you understand the fundamentals of centrifugal pump performance curves and how to interpret them. Understanding these concepts is essential for anyone working with pumps, whether in design, operation, maintenance, or troubleshooting. If you found this video useful, please take a moment to like the video and subscribe to the channel. It really helps support the channel and motivates me to create more engineering content. If you have any questions, suggestions, or feedback, please leave them in the comments section. I'd be happy to hear from you. Thank you very much for watching and have a great day.